Hi, so today's video we're going to pick up where we left off before. Before we were talking mainly about the unit module in the last video. This video will be about what we were calling the class module. And basically what we're going to try to do is just kind of motivate why we're calling it the class module, at least as much as we can. So just to review a little bit of where we were when we left off. A little bit of notational garb. Remember, we're letting K be a finite extension of the rational function field FQ adjoint T. A is the integers, I guess, of FQ adjoint T. It's just the polynomials with coefficients in FQ. OK we're using as the integral closure of A and K, so it's like the integers of K. And K infinity, remember, it's isomorphic to a product of fields, product of completions of V over kind of the infinity adic valuation of K, right? So before, basically we kind of got everything started by looking at this exact sequence of A adjoint G modules. And we know that K infinity sep, this maps, and K infinity sep, remember, is the separable closure of K infinity. We know that from Carlitz's works, we know that the Carlitz exponential maps K infinity onto K infinity sep. Remember, CK infinity sep, what this really is it's the set K infinity sep, but equipped with the Carlitz action now, not just the usual, not just the left multiplication by elements of A, but the A action now on CK infinity sep. This is kind of like that Carlitz exponentiation that we talked about in the first video. So we know that this is an exact sequence. We actually know precisely what this kernel is in this situation, but anyway, but it is just let's just denote it by lambda k. From this exact sequence of A adjoint G modules, we can derive the kind of longer exact sequence of G invariants. So that's what the superscript G means, right? So, and of course, K infinity sep, the G invariants of K infinity sep, those are just K infinity. Oh, by the way, right, we didn't talk about it in the notation, but G, of course, it's the Galois group of the separable closure of K infinity, the separable closure of K infinity over K infinity. So the G invariants of K infinity sep over K infinity are obviously going to be K infinity. Same thing goes on here, and then we get the first cohomology group, H1G lambda K. And then the next guy is going to be 0, essentially because it's the G invariance of, it's the first cohomology group of K infinity, K infinity sep, and that's going to be trivial by basically like an additive version of Hilbert's theorem 90. So, looking at this exact sequence now, recall that we looked at the restriction of kind of this connecting map from CK infinity into the first cohomology group. We restricted it to COK, kind of the Carlitz module of the integers of K. That's going to, just by restriction, map into H1G lambda K, because COK is going to be contained in there. And, before we were talking about the unit module, that wound up, kind of the right analog of unit module wound up being the kernel of this map. But today, and kind of like, as we alluded to before, today we're going to focus on the co-kernel of this map. And the co-kernel of this map, we're going to denote it by HOK, although we could give it explicitly, and this follows easily just from the exactness of these two sequences. But anyway, we're going to focus on the co-kernel of this map, and as it turns out, the co-kernel of this map is going to be a good analog for the class group in kind of the classical setting. So basically what we want to talk about today is why is it that we're calling this class, why is it that we're calling the co-kernel of this map the class module? In what ways is it a good analog of the class group in the classical setting? So before we do that, let's talk a little bit about the class group in the classical setting, and and then we'll pick up, we'll try to relate that to why this is a good analogy. Okay, so let's review some of the classical theorems about class groups, and in particular their relation to zeta functions and L functions and things of the sort. So to start out with, let's let little k be a number field. We're going to let O sub k be the integer ring of little k, and I sub little k, that'll be the group of fractional ideals of k. So for a number field little k, we're going to define the Dedekind zeta function, zeta sub k of s, by s maps to the sum over all ideals of OK of the norm of ideals A of the norm of A to the negative S power. So this obviously converges for complex S greater than 1. And we could also derive an Euler product for S greater than, for real part of S greater than 1, right? But anyway, yeah, so we could also derive an Euler product formation of the zeta sub k of S, right? So, so zeta sub k of S, this can be, oh yeah, by the way, and they call it a Dedekind zeta function because, you know, if you kind of think about what does this look like if k is q, then this looks like the normal zeta function, right? Just the normal Riemann zeta function. So anyway, so as it turns out, zeta sub k of S can be meromorphically continued to all of C with simple pole at S equaling 1 with the following kind of remarkable residue. So the residue ends up being 2 pi to the R2, where R2 is the number of complex embeddings of K into C, times 2 to the R1, where R1 is the number of real embeddings of K into C. H sub k times H sub k times R sub k divided by W times square root of the absolute value of D sub k. And these guys, so W is the number of roots of unity in K. dk, that's the discriminant of K. H sub k, this is the class number of K. So in other words, it's the order of the group of, take all the fractional ideals of K, mod out by the principal ideals of K. H sub k is the order of this group, which always happens to be finite. It's a classical thing. And R sub k is the regulator of K. And R sub k, what it's really kind of measuring is, it's basically kind of measuring the volume of the units if you embed them via a lattice of logarithms into Euclidean space. So yeah, it's interesting that the zeta function, the Dedekind zeta function, encodes so much information about the number field, particularly things about the class group. So yeah, exactly how that, you know, why is it that this analytic object, this analytic function, you know, you might wonder, is there some philosophical reason why it's actually giving you so much information about the arithmetic of K? And as it turns out, there is kind of a deep, philosophical reason to believe, or to kind of understand why it is that these zeta functions, and not only just the zeta functions, but I guess their individual factors, L functions, why is it that they encode so much information about the number field? This is kind of hinted at by the main conjecture of Iwasawa theory, which we'll talk about next. Looking at that residue formula for the Dedekind zeta functions, yeah, you might wonder exactly what's going on there. How is it that this analytic object, this zeta function, how is it tied, or how does it encode information about this algebraic object, namely the one that we're interested in is the class group. Oh, and by the way, you know, it's not only just the residue formula that kind of hints at this. There's many kind of relationships, a lot of things that you can kind of tell about a number field that you can derive from zeta functions. Like for example, in the particular case when K is equal to Q adjoint zeta P, you could look at in this particular case, you can actually look at the negative values of the Riemann zeta function. These wind up being rational, and if you look at their p-adic valuations, that tells you a lot about the p-divisibility of the class group of this guy. So anyway, so there's in many ways the zeta functions seem to tell you quite a bit of information about the class group. So you might wonder, yeah, is there some philosophical reason to believe in this, or is it just some sort of mathematical sleight of hand that just happens to work? So yeah, I think there is a very deep reason why the zeta functions and their associated L functions, there is a deep reason why these encode information about the class group, and that's what we're going to talk about right now. So let's let K be Q adjoint zeta P. I'm just going to work out a particular example here, just to kind of keep things kind of notationally simple. We'll let G kind of break from notation that what you're using before. We'll let G now denote the Galois group of K over Q, so that's Z mod P Z star. We're going to let G hat be the character group of G, and we're going to think of the characters as being actually p-adically valued. So since Z mod P Z star is actually isomorphic to Z mod P minus 1Z, the value group, all the values of these characters are going to wind up being we can think of them as being p-adic integers. So that's going to be the range of our characters. That's how we're going to think of them. And we're going to write E sub chi to be the idempotent associate to chi, where chi is whatever character that we've chosen in G hat. And yeah, like I said before, since our characters are p-adically valued, we're going to view the epsilon chi's as being elements of ZP adjoint delta, where delta is the Galois group of, oops, I don't know why I doubled up my notation there, sorry. So I should have said ZP adjoint G. Okay, this is G. Okay, so right. So speaking of Dedekind zeta functions, as it turns out, they factor into L functions. So we have this identity here. So yeah, zeta sub k of s, this is going to be equal to the product over all chi's in G hat of ls chi, and ls chi is the Dirichlet L function defined by, we can define it as a sum, as the sum from n equaling 1 to infinity of chi of n divided by n to the s. So this makes sense for all reals, all real s greater, or all s whose real part is greater than 1. And we could also give an Euler product for this guy, and it's going to wind up being the product over all primes of 1 minus chi of p divided by p to the s, all to the negative 1. Again, both of these expressions make sense for all s whose real part is greater than 1, but they can be analytically continued meromorphically to the entire complex plane. In fact, ls chi can be analytically continued to the entire complex plane. It's actually it's an analytic function on the entire complex plane, except when the character chi is the trivial character. That's the only time when it actually has a pole, a single pole, a simple pole at s equaling 1. Let's start with our little diagram here then. So we have Q, our base field Q adjoins zeta P, our number field over K has Galois group G. What we want to look at is kind of the cyclotomic tower, the basic cyclotomic ZP cyclotomic extension of Q adjoins zeta P. And by that I guess I just mean, well, I look at Q adjoins zeta P squared, Q adjoins zeta P cubed, in general up to Q adjoins zeta P to the n. And really we're going to kind of think about this as kind of going on forever and ever. We don't think about the whole tower at once. And then for each extension Q adjoins zeta P to the n, we're going to look at the class field that's associated to the CLP subgroup of the ideal class group at every level. So H sub P is going to be the CLP subgroup of the ideal class group of Q adjoins zeta P. HP squared is going to be the CLP it's not going to be the CLP subgroup, it's going to have Galois group isomorphic to the CLP subgroup via the Artin map. And same thing goes for HP squared. HP squared over Q adjoins zeta P squared. This is the class field associate to the CLP subgroup of Q adjoins zeta P squared via the Artin map, and so on and so forth all the way up the tower. And these guys, it's easy to see that they kind of naturally, these guys form a tower as well. So, right, okay. So now what we're going to do is we're going to look at the chi parts, the epsilon, the chi parts of each HP to the n, and we're going to look at the inverse limit of epsilon chi HP to the n. And the inverse limit is by taking norms. These guys are kind of coherent via the norm map. And as it turns out, this inverse limit is essentially like a gluing together of all the chi parts of the CLP subgroups of the ideal class groups through this chain. As it turns out, this guy is a kind of naturally a ZP adjoint gamma n module, where gamma n is the Galois group of Q adjoint zeta P to the n over Q adjoint zeta P. You just let gamma n kind of act on the HP to the n part. The ZP action makes sense since each of these guys is exponent of prime power. So yeah, so the action is kind of coordinate-wise. Or you could think about, actually, as it turns out, this guy is actually isomorphic to the power series ring in T. So you could think about this as actually being, you can think about this guy as actually being a ZP adjoint T module, a module over the power series ring with p-adic coefficients. So, right, okay. So then that means, as it turns out, as a ZP adjoint T module, this guy is pseudo-isomorphic to a finite direct sum of things of this type. So this is kind of like, it's almost like a decomposition of. But it's reminiscent of decomposition of modules over a principal ideal domain. The pseudo-isomorphic, that just means that there is a map from this module to this module with a finite kernel and co-kernel. So that's what pseudo-isomorphic means. So, so yeah, this is a finite index, and these GIs, these are actually polynomials, they're not power series. They're actually distinguished polynomials in ZP adjoint T. So yeah, also, as it turns out, there exists a power series in T that depends on chi, that lives in our power series ring ZP adjoint T, such that LPS chi is actually equal to kind of a twisted version of this power series. So in other words, so yeah, basically our LPS chi, this is equal to f of 1 plus p to the s minus 1 chi. And the dependence on chi is because it's associated to this to the p-adic L function associated to chi. Oh, and by the way, yeah, LPS chi, this is just a p-adic interpolation of LS chi. And by that I just mean it's a p-adic analytic function that takes kind of the same values at negative integers as LS chi does. So, so with all this information, I know that was awfully dense, but we get this amazing, so now we've kind of set up all this machinery, we get this amazing fact. And the fact is that if you look at the product of GITs, and that's what basically what this product is, it's the characteristic of this module, which is essentially our module of class groups, of p parts of class groups, right? So when we look at the characteristic of this module as a ZP adjoint T module, as it turns out, it's basically equal to a p-adic L function. And that's just mind-blowingly great. Like, whenever anybody says anything about how math is so beautiful, this is usually what I automatically just kind of think of. It's like, what could be better? Like, you know, when you first start looking at L functions and zeta functions, you notice that their value, the values that they kind of give at special values, like negative integers, they give you a lot of information about class groups of the various fields that they're associated to. And you know, you're kind of sitting there wondering, what's going on? Is this some sort of voodoo, or you know, well, why? You know, is there some deep philosophical reason why this should be so? And this is kind of like saying, yeah, there is. The p-adic L functions are actually the characteristic polynomials, essentially, of our modules, of the modules of the p parts of the class group. So it's like, so yeah, no wonder these things are giving you such great information about the class groups of the various fields that they're associated to, right? They're essentially, it's like the most straightforward annihilator that you could write down of a module, right? So, so yeah, this is just kind of an amazing fact, and this is called the main conjecture of Iwasawa theory. And it's, yeah, it's a reason to believe why L functions and zeta functions are important as far as studying kind of the arithmetic of the field. So yeah, what do we expect, or at least what do we expect a characteristic p-valued analog of a zeta function to look like? Well, the functions themselves can be kind of complicated to describe, and as far as today is concerned, all we're really going to care about is what's going on at a special value. So let's see if we can't write down that analog, right? Well, I guess the most straightforward thing you could write down is basically something like this. So zeta function evaluated, and the special value we care about is evaluation at 1. Yeah, this seems to be, you know, in comparison with the number field setting, this seems to be kind of the correct analog, or the most straightforward thing to kind of write down, right? The sum over all ideals of OK, of the A fitting ideals of OK mod A inverse, right? And what the fitting ideals are is, well, OK mod A, this is an A module, so it's going to decompose, and say is a PID, it's going to decompose into a finite product or finite sum of quotients of A, things that look like A mod F sub I or something like that. And so taking the product of the F sub i's, that's what this fitting ideal is. It's a monic generator of the characteristic of this guy as an A module. Oh, and you notice in contrast to the number field setting, we actually don't need to take, we can actually evaluate this at 1. This guy actually converges in little k infinity, right? So all these guys, the members of the sum, these are elements of little k. Convergence will happen in little k infinity, the infinity-adic completion of little k. So yeah, we don't need to take residues. We can actually just evaluate. But this is, this is the most straightforward analog of the residue at s equaling 1 of in the number field setting. Right? Remember, in the number field setting, we could actually rewrite, instead of using the norm of A, we could actually rewrite it, if you felt like it, as the Z fitting ideal of OK mod A to the negative S. right? Okay, so what do we expect to say, or what do we expect out of this this zeta value, or this? What do we expect out of this special value? Remarkable theorem by Lenny Taelman says that this value, zeta OK, is actually equal to the A-fitting ideal of k infinity modulo our lattice of logarithms, that's our black bold U from the last video, divided by the A-fitting ideal of k infinity divided by OK. So this guy's like a regulator, this guy's like a discriminant, and then we have the A-fitting ideal of our HOK, right? And so this kind of explains why we're actually calling HOK the class module, right? It's by virtue of the fact that you're kind of tempted to say that this should be the class module from this, or that HOK is the right analog, the right correlates analog of the class module by virtue of the fact that this formula holds, right? I mean, this is almost an exact analog of what happens in the number field setting, right? We saw in the very beginning that the residue at s equaling 1 of the Dedekind zeta function, that this was related to the regulator and the class group, right? So in the same way that this special value is related to the modules that we've been talking about, that's kind of, you could take that as kind of inspiration. That's why HOK is the proper analog of the class module. So yeah, just to kind of sum everything up, I mean, so these characteristic p-valued analogs of zeta functions, they've been around for a while, and they were originally discovered or invented, depending upon your point of view, to help kind of investigate the correlates module. So perhaps it shouldn't become as any surprise that the special value at 1 should be related to kind of to the right kind of to the right analogs of the class module and the unit module, right? So you can think about this sum is actually quite complicated. It's difficult to actually kind of take the sum in the same way that it's for example, it's difficult, say, to evaluate the sum of evaluate the Riemann zeta function, say at even integers. I mean, or I'm sorry, at odd integers. It's very difficult. There's not like a closed formula for it or anything like that. But here, like you actually know exactly what this is now, right? It's precisely these things. You've related this guy. It's amazing that you can relate this characteristic special value of the zeta function to the modules that we've been talking about. So, and it's also amazing just the fact that, on the one hand, we've written down this zeta value, the special zeta value, as the most straightforward analog that we could have written down just taking inspiration from the classical sense. It's amazing, though, that this seems to be saying something about the correlates module. You might suspect that maybe this would say something about kind of like the naive class group in the function field setting. It's kind of it's surprising, I think, at least to me, that it actually seems to be encoding information not about kind of the naive class group in the function field setting, but about this class module, right? So yeah, that's kind of an amazing thing, and yeah, I think work is still ongoing into how much what about the other zeta values? What relations do they have? I think this work is ongoing.